So with this podcast, we're going to just cover the rest of what's in the notes that you already have in your summer packet. But the first thing is just KMT, which is Kinetic Molecular Theory. And gases were really the first types of molecules that chemists began looking at and studying. And they kind of came up with ways to describe things they saw macroscopically, but things they couldn't see at the microscopic level. All right? So here are the postulates, and they're listed in your notes. But the first thing is molecules are point masses, which means they have point masses, so they're just kind of a point in space, but it really doesn't take up any volume. So just kind of a pinprick of mass that has mass, but it doesn't really have volume. We know this to be false, so I'm just going to highlight this as being false, because matter is anything that has mass and volume. So if gases don't have volume, they're not matter, but they are in fact matter. So just know that number one is false. Number two, molecules move randomly in all directions at varying speeds. Completely true all the time. Number three, attractive and repulsive intermolecular forces are negligible. So again, this is false. Most of the time though, under normal conditions, this is true. So if the temperature is relatively high, which we might say room temperature, which is 25 degrees Celsius, the molecules are moving so fast past each other. They're moving hundreds of meters per second. So because they're moving so fast, if you have magnets and you push them past each other really fast, there's really no attraction because their momentum overcomes that attractive force. However, if they're going slowly and they are lined upright, they snap together or they repel each other. So kind of the same idea with gases. There can be intermolecular forces between gases, which is why we can actually condense gases into liquids and then freeze liquids into solids, is because of attractive forces. But the postulate says these are negligible. And again, that's mostly true, but it's actually false. Number four, collisions are elastic, which means there's no loss in average kinetic energy. So if you're thinking about gas molecules and they hit each other, when they hit each other, do they slow down? And we say no. When they're going through, as they're moving through space, or whatever you want to call it, is there anything between them? And there's not. There's no friction between gas molecules, because usually we say there's air friction, but they are the air. Alright? So again, collisions are perfectly elastic. And then this one is really good. Average kinetic energy. And this funky sign right here just means proportional to temperature. And again, you should have this in general chem or honors chem. Just drilled into your head that the average kinetic energy of something is related to its temperature. So if the temperature is high, molecules are moving fairly rapidly. If temperature is low, the molecules are moving much more slowly. So ideal gases are completely imaginary, but they make our math really, really easy. So ideal gases, we say, follow all postulates all the time, which is false because two of our postulates are not true. So real gases follow KMT except when the gas molecules are really close to each other. And that happens, well, you might say very close to each other, or moving slowly. So I'm just going to come in here and actually add this to notes if I can. That's not going to let me. Or moving slowly. Alright, so this happens under two conditions, which I'm going to hit that. Alright, and this is extremely important, so we're going to highlight this. So they are really close together when the pressure is really high. So when pressure is high, that means volume is low, so they're compressed really close to each other. So when they're close to each other, what's true about their attractions between particles? Well, if they're close, they're not only going to have attractions because they're really close to each other and they're kind of locked in place. They're either going to attract or repel each other. But the other thing is their volume. If the gas is taking up, normal pressure, there's a lot of space between our gas molecules. But if that pressure is condensed, even though their volume is really small, their volume becomes significant if the overall volume is really, really small. So high pressure means small volume, which means we have issues with number one and with number three. The other one is if they're moving really slowly. We already talked about the magnets. So if they're moving slowly, they're more likely to attract or repel each other. So if they're moving slowly, that means our temperature is very low. So again, these two situations, high pressure, low temperature, which equals low volume for the pressure, real gases deviate from ideal gases. There's an equation that's called the van der Waals equation. You don't need to know how to use it, but it's an equation that allows us to calculate how far ideal gases deviate from real gases. All right, the next thing we're going to look at is just some of the topics that are in the rest of your packet. One of them has to do with, I'm trying to think, I'm going to go cheat real quick. Gas stoichiometry, we're not going to worry about until we get to gases. All right, effusion and diffusion. We've done a little bit of this already, and it's simply the idea that we can compare two gases at a given temperature. So let's say I want to say how much faster is helium than hydrogen, or how much faster is hydrogen than helium, because hydrogen weighs less. So if I do hydrogen and compare it to helium, it's not going to be hydrogen has a molar mass of 2, helium has a molar mass of 2, so hydrogen is twice as fast as helium. It is inversely related, but it's an inverse square root. So we're going to do the molar mass of helium, which is about 4, over the molar mass of hydrogen, which is about 2. So we would have hydrogen is, I don't know what the square root of 2 is, it's something I should know, 1.4 something, 1.6 something, whatever that is. So it's 1 point, I'm going to make this up, 6 times faster than helium. So helium is just going to be 1 time for every 1.6. So it doesn't tell us their speed, but it tells us a ratio of their speeds at a given temperature. We can always use the root mean square to calculate actual speed of a gas at a given temperature. The other thing we can look at real quickly is Dalton's law, which is fairly straightforward. And he has this law named after himself, and it's pretty much straight common sense, which is ridiculous. So anyways, Dalton's law is just the total pressure of gases is equal to the sum of our partial pressures. So if we have a bunch of gases together, if we add up their pressures, so the pressure of 1 plus pressure of 2 plus pressure of 3, the sum of those equals the total pressure of our gas. And we can have as many gases as we want, so just dot, dot, dot. That really sums up gases, KMT, comparing effusion or diffusion rates, and then Dalton's law of partial pressures. Another thing just to be familiar with is probably the stuff right in here, molar mass and density. I think that's fairly easily worked out here, how to solve for molar mass and density given pressure, volume, temperature, and mole values. So anyways, those two podcasts, gas laws in R, plus this one, which is KMT and effusion, and that should do it for the summer podcasts.